Let's take a look at example number 11. Batman needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet, and from the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. Okay. Let's see, what is that going to look like? Okay, so here's the ground. There's some tree, which I'm going to assume is completely vertical, so it's going to form a 90-degree angle with the ground. Okay, but here's our tree. And Batman is standing some feet away. Okay, so let's just say he's standing here. That looks more like a Catman, but it's okay. So that's Batman there. And it says that from that point, he finds that the angle of elevation to the top of the tree is 36.7 degrees. Okay, so let me just draw that angle of elevation. So this first one, 36.7 degrees. He then moves back 50 feet. So let's just call this point A, the first point at which he takes the measurement. He then moves back 50 feet. So somewhere over here, let's call it B. And at that point, the angle of elevation to the top is 22.2 degrees. So let's see. So now this angle here is going to be 22.2 degrees. Find the height of the tree to the nearest foot. So what we're interested in finding is that height there, which I'm going to call H. And I forgot to label this distance between the 2 points. It's actually 50 feet. Okay, so how can we relate this? Again, so far the only thing that we know how to solve for are right triangles. So let's look for all of the right triangles present in this diagram. One right triangle would be the one that gets formed between this angle of 36.7 degrees and the height, right? That's the first triangle. So let me actually draw that separately. And so we have something like this. Oops. That's the first one. The other right triangle that we have is the one that gets formed with the 22.2 degree angle. So it's this outer one. And I'll draw that one as well. Okay. Other information that we're missing, well, this is point B, this is point A. Since we're looking at the inner triangle here, that's point A. And then this one would be point B. Okay, now I don't know this adjacent side, how much it measures, so I'm actually going to give it a name. Let's call it A for adjacent. And so this bottom adjacent side is the same as the one we have here. We're calling it A. That means that this whole adjacent side for the 22.2 degrees is going to be this measurement of A plus 50 feet, right? Because technically there's A, the point A somewhere here, and this measures A, this measures 50. So together they make up A plus 50. So I'm going to simply write that here. This is A plus 50. We can even color code it if you'd like. So it's going to be this bottom side. That's A plus 50. And now we want H, right? Let's see what each of these triangles gives us for H. If I use this first one, again, I have opposite side and adjacent side. So from the first triangle, what we get is that tangent of 36.7 degrees is opposite, which is H, over adjacent, which is A. Solving for H means that I multiply both sides by an A over 1. And we get that H will be equal to A times tangent of 36.7 degrees. Yeah, that's from triangle number 1. From triangle number 2, and I'll draw a separating line here so that it doesn't get confusing as to where the equations are coming from. But for triangle number 2, I also have in relationship to angle 22.2 degrees, opposite and adjacent side to deal with. So this one would give me tangent of 22.2 degrees is equal to opposite, which is H, the opposite side, over adjacent, which is A plus 50. And if we want to solve for H, in this case, we're going to have to multiply by an A plus 50 over 1, because that's what's found in the denominator. Yeah, so here I'm going to have to multiply A plus 50. Doesn't quite fit, but I'm going to draw a little arrow to say A plus 50 gets multiplied to 10. By the end of that multiplication, we'll end up with H is equal to A plus 50 times tangent of 22.2 degrees. And on the right-hand side, these cancel out because that's what we intended to do. All right, so what then? Well, now we have two equations. Both of them are dealing with H, but we also have an unknown A as part of each equation. Now, because we have two equations with two unknowns, from algebra, we know that makes a system of equations and that we should be able to solve it. So one way or one method that they taught you in algebra is to use substitution, meaning to solve one of the equations for one of the two variables and then replace the expression into the other equation. So that's what we're going to do here since both of these are already solved for A. What I'll do is, let me call this equation 1. And this is equation 1, and this is equation 2. What I'll do is I'll replace the statement from 1 for H into 2. Okay, so plug in 1 into 2, and what do we get? Well, I'm going to get that A tan of 36.7 degrees is equal to A plus 50 times tan of 22.2. Now, once I've done that, I have only one unknown. It's A. All right, I have one equation with one unknown, and we know how to solve equations with only one variable. We simply isolate the variable. Now, what might seem intimidating in this problem is the fact that we have the tangents there. But don't let that scare you, because you actually know how to solve these types of equations. So for instance, let's say that instead of tangent of 36.7, which is a number, right? We just need to punch it into the calculator to see what number it is. But let's say I were to replace that with some constant. For example, what if instead we had a times 3, which is 3a, is equal to a plus 50 times, let's say this is constant 2, okay? How would we solve this? Well, we'd say, well, first I need to get rid of the parentheses. I would need to distribute the 2 into the a and the 50. So we'd have 3a is equal to 2a plus 50 times 2, which is going to be 100. And then once we've done that, I would subtract the 2a from both sides because we need to have like terms. So let's take this first step before we subtract the 2a. Let's take this first step of distributing the 2, the constant, in our problem, which is actually tangent 22.2, to get rid of parentheses. And so I'm going to do this. Distribute tangent to the a and tangent to the 50. And we'll get nothing changes on left-hand side. It's still a tan 36.7 degrees is equal to a times tangent of 22.2 degrees plus 50 times tangent of 22.2 degrees. Okay, so now we're basically at this step where we have dropped the parentheses. What would we do from there, we said, to this equation? Well, we would subtract the 2a from both sides to get all of the terms that have a variable on one side of the equation. And so the result of that is, here it's easy because it's 3a minus 2a, which gives me 1a. But technically what we're doing is this, right? Just to write out what's happening, we're subtracting 3a minus 2a, and then here the 2a, negative 2a cancel out, and we get that equals the constant only of 100. Well, we're going to do a similar thing here, where I'm going to subtract the a tan of 22.2 from both sides of the equation. That way I have everything, all the terms that have an a on one side, on the left-hand side, and constant left by itself on the right-hand side. Okay, so let's do that. I'm going to subtract a tan of 22.2 degrees, subtract a tan of 22.2 degrees. And we're going to get on the left-hand side a times tangent of 36.7 minus a times tangent of 22.2 degrees is equal to, these are gone, just 50 tan of 22.2 degrees. Okay, now that I have a present in both of these terms, well, what I can do is factor it out. Okay, so if we factor it out, we're going to get a times tangent of 36.7 degrees minus tangent of 22.2 degrees is equal to 50 times tangent of 22.2 degrees. Now we can solve for a by dividing through by this constant. Remember, this is going to evaluate to some number, so it's just a constant. We'll divide both sides by it. These are gone, and we're left with a is equal to 50 times tangent of 22.2 degrees divided by this difference, tangent of 36.7 degrees minus tangent of 22.2 degrees. Now remember the difference. I'm encompassing with parentheses because I need to make sure that the whole thing gets placed under the denominator and not just the tangent of 36.7. And unfortunately, I've run out of room, so I'm going to use the second sheet to continue the work. but let's see. Do we want to punch into the calculator at this point? Well, what was the original goal? The original goal, if we go back up, was to find the height of the tree. A is not the height of the tree. A is this part here. So I'm really interested in H, which in this first triangle was given by H equals A times tangent of 36.7. Or if you want to use a second triangle, then H is given by A plus 50 times tangent of 22.2. So I'm going to use this equation because I don't have to deal with the plus 50 part. It's just whatever expression we got for A times this tangent of 36.7. But if you were to use this second triangle, you'll see that we'll get the same answer, but I'm not going to do it. You're welcome to punch it into your calculator if you are interested in verifying it. Okay, but let's see. So then from equation 1, I'm going to plug this into equation 1. By A, I mean this here. Okay, so plugging it into 1 is going to give us H equals, let me just write the original expression first, A times tangent of 36.7 degrees, which equals 50 times tangent of 22.2 degrees divided by the difference tangent 36.7 degrees minus tangent 22.2 degrees multiplied with, so this, all of this is A. And so all of this stuff here is A. And then multiplied with the tangent of 36.7 times tangent of 36.7 degrees. Okay, now this is like multiplying by tan 36.7 over 1. So I could multiply the numerators together and the denominators together. In the numerator, what I'll get is a 50 times tangent of 22.2 degrees times tangent of 36.7 degrees, all divided by tangent of 36.7 degrees minus tangent of 22.2 degrees. So now we punch into our calculator. We're going to get, in the numerator, let me just go ahead and encompass it with parentheses. 50 times tan, times tan of 22.2 multiplied with tangent of 36.7. Close the parentheses for the numerator. Then divided by, open parenthesis for the denominator now, tangent of 36.7, close the parenthesis for 10, minus tangent of 22.2, close the parenthesis for tan, and then close the parenthesis for the denominator. So this closes that open parenthesis. And we get approximately 45 feet. They do ask us to round to the nearest foot, so that means that the height is approximately 45 feet. For these next couple examples, we're going to need to know what bearing means. So bearing refers to the direction of motion of an object. For instance, a ship or an airplane or a car, a bicycle, someone walking, anything that's moving is, when we're trying to describe the direction of motion, bearing would be what is used for that. And we always describe that direction of motion relative to another object. Now, there are two ways that they can give you the bearing of a moving object. If only the angle is given. So for instance, let's say that they tell you, they give you some description and then they say on a bearing of 34 degrees, let's say. Now they only give you the angle. What's to be understood from that is that you're starting, you're moving away in a clockwise direction from the north direction. So let me draw the four directions. So this is north. Here's east. South and west. And so if they only give you the angle, then you start from north and open clockwise. Okay, so this would be a bearing of 34 degrees. Oops. Okay, that didn't quite go as well as I wanted it to, but let me just erase this arrow and have it terminate there. All right. So in general, opens clockwise starting at north. Now, if the initial direction is given, they're also going to give you the direction towards which it is opening. So for instance, they're probably going to write something like maybe on a bearing north, and let's say 55 degrees west. Okay. So the initial bearing is always the starting, and it's either going to be the north or south directions. Okay, so it's going to be one of these two in the vertical direction. Then it's going to give you the number of degrees followed by the bearing towards which you should open. So this one is saying start at north and open towards west, 55 degrees. The way that this is read is 55 degrees west from north. Okay, so here we would say opens away from north, 55 degrees towards west. That would look like. Would be like this. Okay, so start at north, go towards west, 55 degrees. Start on north, open towards west. And when only the direction is, when only the angle is given, you always start at north and you open clockwise. Okay, so let's see an example that involves bearing. Radar stations A and B are on an east-west line, 3.7 kilometers apart. Station A detects a plane at C on a bearing of 62 degrees. Station B simultaneously detects the same, this should say plane, on a bearing of 331 degrees. Find the distance from A to C. Okay. Let's start with drawing the east-west line. Okay, so here's my east-west line. And we have two radar stations, A and B, on that east-west line. They tell us they're 3.7 kilometers apart. Okay, so the distance between them is 3.7. Plane or station A is going to detect a plane at some point C, which is on a bearing of 61 degrees. So notice here they don't tell us what the initial direction or ending direction are. They just say on a bearing with some angle. That means that we're starting on north and opening clockwise. So let me just draw the four directions. This is going to be, this is going to be north. This is east, south, and west. Okay, on a bearing of 61 degrees, if we open 61 degrees from north in the clockwise direction, it'll bring us approximately there. Now they don't mention how far away that is, so I'm just going to go ahead and draw some extending line, but it's C, the plane at C is somewhere on this line. Now to pinpoint exactly where that is, we can take a look at what station B is detecting. It's detecting the same plane on a bearing of 331 degrees. So relative to this point at B, if we draw the four directions again, which are north, east, south, and west, relative to this one, it's detecting the plane on a bearing 331 degrees. So again, that means from north, open clockwise 331 degrees. So that's almost 360 degrees, right? If we complete it all the way up to the north direction, that again would be 360. But we're at 331 degrees, which means that it's detecting the plane somewhere on that bearing. So if this is happening simultaneously, if these two radar stations are taking these simultaneously at exactly the same time, then we can say that at the point at which both bearings intersect, that is where the plane is going to be. Okay, that's plane C. Okay. And I'll just go ahead and draw this in red because that was the terminal side of this first angle. And this was the terminal side of this second angle. Okay. All right. So they want us to find the distance from A to C, which is this distance. Let's see what we can find out about the angles and see if that aids us in finding what this measurement is. Okay, so I'll go ahead and redraw the same triangle, but down here separately without the directions, because these are a bunch of letters that might confuse us. So I'm just going to draw the triangle by itself. Okay, this is A, B, and C now, and 3.7 kilometers between the two radar stations. Now the what I didn't label here were the angles. So let me label this. This was 61 degrees. They told us it was on a bearing of 61 degrees. This was 331 degrees. And I'll color code those as well. That way it's easy to read where they are coming from. Okay, so that's 61 and let's say this one here, I'll use green for it. This one's 331. Okay. Now to find this angle, which I want to say is angle A, what can I do about these two angles? What do they sum up to? Well, together they make up the 90-degree angle, right? So from here, what I can see is that 61 plus the angle A should be 90 degrees. So I'm going to do a little bit of side work for this. And I'll do it maybe up here. So A plus 61 degrees should be 90 degrees. If I subtract 61 from both sides, I'm going to get that A is 29 degrees. So down here, this measures 29 degrees. Okay. Now, on the other hand, we have, this is 331 degrees. So the angle here that gets formed would have to be 29 because together they make up 360. Now I'm not interested too much in this angle. What I'm interested in finding is this inner angle, angle B, the one down here. So in order to do that, what I can see is that 29 degrees plus angle B give me 90. So B plus 29 degrees is 90 degrees. So that means that B is going to be 61 degrees. And down here, this is 61. And then what else do we know about the sum of the angles in a triangle? Well, we know that when we have A plus B plus C, that it should give us 180. And so if A is 29 and B is 61, and we add it to C, and that gives us 180, 29 plus 61, that's 90 degrees. So 90 plus C gives us 180, means that C has to be 90 degrees. Okay, so that's actually pretty useful because what that tells us is that this is a 90-degree triangle, a 90-degree angle, which makes a right triangle. And if we are trying to find the side AC, this distance, that's the ultimate goal, to find the side AC, then I could use the definitions of the trig functions to help me out. I can either use angle A, and since this side is adjacent to angle A, I could use cosine of 29 as the adjacent side. Let me call this little b since it's opposite to angle B. Okay. I could use cosine of 29 degrees is adjacent over hypotenuse. And this is a hypotenuse because it's opposite to 90 degrees. So let's do that. Cosine of 29 degrees is equal to adjacent over hypotenuse. The adjacent side is B. So cosine 29 degrees is B over hypotenuse, which is 3.7 kilometers. If we want to solve for B, that means multiply both sides by a 3.7 kilometers over 1. So that's just a 3.7. We're going to get that B equals 3.7 times cosine of 29 degrees. If we punch it into our calculator, and I encourage you to do that on yours, we're going to get approximately 3.2 kilometers for B. So here I've decided to use angle 29. You could have used angle 61 if you prefer, and then use sine because the opposite side is the one that we're interested. So it would be opposite over hypotenuse, and that gives you sine. Okay, so sine of 61 degrees is B over 3.7, and then multiply both sides by 3.7, and you'll get exactly the same thing. One more problem involving bearing. This one reads, a ship leaves port and sails on a bearing of 47 degrees east from north for 3.5 hours. It then turns and sails on a bearing of 43 degrees east from south for 4 hours. If the ship's rate is 22 knots, which means miles per hour for a ship, find the distance that the ship is from port to the nearest mile. And of course, there is an apostrophe missing here that you can include. Okay, I'm going to start by drawing the port and then the bearings, the bearing on which the ship has sailed. So let me start by writing this point P, and well, actually, let me use a different color for it. I'll use purple since we've been using blue for the bearings. Okay, so that's our port, point P. And on this port, relative to this port, we'll have the 4 directions. Oh, and I'm going to have to label P somewhere else. Okay, so north, east, south, west. Here's our port. Relative to that one, a ship leaves port and bears 47 degrees east from north. So that means that start at north, go towards east, 47 degrees. Okay, so that is going to be approximately there. And it travels in that direction for 3.5 hours. It then turns and sails on a bearing of 43 degrees east from south. So from this point, this new point, which we're going to call, let's call it B, we have a change in bearing. So if we draw the 4 directions there, and unfortunately, I should have probably drawn this a little bit lower so it doesn't go over into the directions, but that's okay. We'll make the best of it. So here's north, here's south, here's west. So from this point, the ship sails 43 degrees going towards east away from the south direction. So now starting at south, we're going to go 43 degrees east. Okay, so it's going to end up somewhere maybe about there. Okay, so that is 43 degrees. Now we are interested in finding the distance the ship is from the port to the nearest mile. So we're interested in this here. I'm going to call this point A. Okay. So like we did earlier, I'm going to redraw this triangle, focusing only on the angles and the sides, because there is quite a bit going on with all of these directions in the diagram as it is. So let me just redraw it really quick. I'll have P, I'll have B, and then I'll have A. We can find out what, okay, well first we can find out what this angle is, and here's how we can do that actually. There are two parallel, the north and south lines, the north-south lines of the 2 points, at the 2 points make up a pair of parallel lines. And then I have this traversal that's passing through them. And so remember what we said about parallel lines that are intersected by a traversal? We said the opposite interior angles are congruent. So that means that this angle here that gets formed between south and that terminal side has to be 47. Okay, so this here is 47 degrees. And now if we take the sum of these two angles together, the 47 plus the 43, we actually get 90 degrees for this angle B, which is nice because now we're working with a right triangle. Okay. Is there anything else that we might be able to find? Well, they do tell us how fast the ship is traveling and how long it's traveling at that speed for. When it's sailing away from the port initially, and I've mislabeled this, it should be P. When it's traveling away from the port initially, it travels in this direction at a rate of 22 miles per hour for 3.5 hours. So the distance here, which, and I think I also mislabeled this, apologies, this should be A. Okay, so it's P, B, and A, P, B, and A. So this distance here, which I'm going to label little a is going to be given by a 22 miles per hour times 3.5 hours. So the hours are going to cancel out, and we're just going to be left with miles. So A is 22 times 3.5, which is going to give us 77. And that's in miles. Okay, so this here is 77 miles. What other information do we know? Well, we know how long it was traveling from when it first turned to the last point that we were interested in. It says it then turns and sails on a bearing 43 degrees east from south, so this bearing here, and it travels at in that bearing for 4 hours at 22 knots. Okay, so I'm going to call this little p because it's opposite to angle P, and little p is going to be 22 miles per hour times 4 hours. So again, the hours are going to cancel out, and we're just going to get that P is 88 miles. Okay, so this is 88 miles. Now, what were we interested in finding? We're interested in finding the distance that the ship is from the port. So this distance here, that is distance B. Now, what can you guys tell about that distance? Notice we have a right triangle. In this right triangle, we have both of the legs. We're just missing the hypotenuse, which also happens to be the distance between the port and the ship. So we can apply Pythagorean theorem here because we have all the information that we need for it. Okay. But just to repeat what I had mentioned earlier, the distance then is going to be given by distance squared equals a squared plus p squared by Pythagorean theorem, because this is a right triangle. We are given the two sides. So a is 77, p is 88. So that means that the distance will be the square root of those two quantities added together. And then when you punch it into your calculator, you get approximately 117 when we round to the nearest mile.